Okay, so I am recording manually using my phone. Okay, so you may start.
Okay.
So
Okay.
we
So
start
it's you can see my slides right now,
yes,
right?
yes, I am.
Okay. Okay. Good morning, everyone. My name is Hebah Saleh Al-Sagabi, and today I will be presenting my PhD work titled "New Secure and Efficient Elliptic Curve Based Crypto System and Signature Scheme," under the supervision of Associate Professor Dr. Edi Shahril Ismail. In this talk, I will explain the motivation behind my research, outline the problem with existing elliptic curve scheme, and show how my proposed crypto system and signature scheme aim to provide both strong security and high efficiency, especially for constrained environment. Elliptic curve cryptography, or ECC, plays a central role in modern security because it offers high security with relatively small key sizes. This makes it very suitable for devices with limited resources, such as IoT devices and smart cards, also embedded systems. In practice, encryption and digital signature are usually provided by separate systems. Encryption protects confidently, while signature provides authentication, integrity, and non-repetition. My research is motivated by the idea of designing ECC-based mechanism that can deliver these functions securely and efficiently in more unified way without adding unnecessary computational or communication overhead. Although many elliptic curve-based crypto system and signature scheme are more efficient than traditional public key systems, they often rely on informal security arguments and limited threats models. In particular, some scheme claim security based only on hardness of elliptic curve district logarithm problem without rigorous proofs under standard notation such as IND, CCA for encryption, or EUF, CMA for signature. At the same time, their efficiency analyses are often theoretical and do not fully optimize performance in constrained settings, and using multiple separate systems, increasing implementation complexity. This motivates the need for a new elliptic curve-based crypto system and signature scheme that are both formally proven secure and carefully optimized for efficiency. The overall aim of my research is to achieve a secure, fast, and unified ECC model suitable for constrained system. In particular, the first objective is to design a new secure and efficient crypto system and a new digital signature scheme based on elliptic curves, which has already been completed. The second objective is to analyze the security of this proposed system under various cryptographic attacks, including IND, CPA, and EUF, CMA, and this work is in progress. The third objective is to evaluate the efficiency of the crypto system and signature scheme using computational time complexity to demonstrate that they are practical for real-world development. For the proposed crypto system, I first defined the elliptic curve environment by selecting a large prime P, constructing the finite field, and choosing secure curve parameters and a base point of a prime order. The receiver's private key is a random scalar, and the corresponding public key is obtained by scalar multiplication on the base point. To encrypt a message, the sender chooses a fresh random value, computes an ephemeral public point and a shared secret with the receiver's public key, and then masks the message using one coordinate of this shared point to form the sphere text pair. Decryption is performed by recomputing the same shared secret with the private key and then recovering the original message from the sphere text, which ensure confidently with relatively low computational cost. The proposed digital signature scheme is also built over the same elliptic curve parameters and uses a hash function that maps arbitrary length messages into the appropriate integer range. The signer's private key is a scalar, and the public key is again obtained by scalar multiplication with the base point. To sign a message, the signer picks a random value, computes commitment point, derives a hash of the message combined with this point, and then forms the signature component that binds the message. The randomness and the private key together. Then the last step is the verification, where the verification is done by recomputing the hash and checking a simple elliptic curve equation that relates the signature, the commitment, and the public key. If the equation holds, the signature is failed, which provides authentication and integrity. PhD research timeline. In this slide, you can see it summarized the timeline of my PhD research activities, with the literature review and the design of the elliptic curve-based crypto system and signature scheme are planned for the completion by the early 2026. The subsequent months are dedicated to formally analyzing the security of the proposed scheme under the different attack models and then evaluating their efficiency in terms of computational performance. Finally, the remaining period is allocated to completing the thesis writing and preparing the draft for submission. So to conclude, this work proposed a new elliptic curve system based crypto system and digital signature scheme, designing specifically to balance a strong formal security with a practical currently analyzing their security under standard notation like IND-CPA and EUF-CMA, as well as evaluating their computational performance. In the next stage of my PhD, I will focus on completing these analyses and demonstrating that the proposed model can be a practical candidate for real-world secure application in IoT and similar environments. Thank you for attending and listening for me today.
Thank you, Hebah. Hebah, in your research timeline, do you notice that in your plan you aim to finish less than 1 year? You
Yes.
aim to complete the PhD less than 1 year.
Yes.
I am not sure if you are able to graduate this short time, because I believe that there is a minimal period to complete PhD.
Yes, I understand, but I'm not. This is not the first year for me.
Okay.
I start before like this. Now this is almost the second year for me here.
Oh,
Or
okay.
the third one.
Because you state in your timeline that you start PhD in January?
No, only the literature review I start. Before that, we reading a lot of papers with that my supervision, and we do a lot of works. But I start the literature review in this time.
Okay. Actually, Hebah, literature review is work with reading papers.
Reading papers. I know.
So you should mention here that literature review start at the very early of your PhD. Okay.
Yes.
And
yes, it's gonna be more clear. Yes.
In your plan, okay, you have complete objective 1, objective
Yes.
2 and 3. Objective 2 and 3 are going to be completed within 6 months.
Yes.
So 3 months for each objective. So this period is quite short relative to the compared to the computing the algorithm.
Yes.
Do you think it is doable? Complete the analysis and analysis of the security and evaluate the efficiency within 6 months?
According to a discussion with my supervisor, Dr. Eddie, he said we are able to do this, inshallah.
If you are guaranteed, if you are confident enough that your crypto system, crypto system is good enough. Okay, so let us go to your you did say something about a work that motivates your work. What are the existing work from the literature review that motivates your work? Motivates you to compute with this new crypto system and digital signature scheme? What motivates you?
Actually, my goal wasn't to replace the existing ECC, but to design a unified and provably secure and efficient also framework whose security and performance properties are clear, also analyzable and suitable for constrained environments. So basically, my work is proceed with the work is already done by the researcher these times. So it just improvement.
So I want to know what is the difference between your work and existing crypto system? How does it different?
Okay. The existing ECC scams are often designed separately for encryption and signature, and many only gives informal security. In my proposal, I designed a unified ECC crypto system and signature that share the same curve parameters and use very simple operation. Both are intended to come formal security proofs. The encryption with a reduction of the elliptic curves district logarithm problem. So my scheme will avoid expensive operation such as modular inverse and in the signing step and use a small fixed number of a scalar multiplication. So
Hebah, you need.
So I can say that the system which I will propose is gonna be stronger and more explicit security guarantees than many existing ECC-based proposed, while being very suitable for constrained environment like IoT devices and embedded system.
Hebah, we cannot guarantee the efficiency, the security is good enough until you complete objective 2 and 3, right?
Yes, of course.
So,
I can, yes.
If the proposed crypto system do not achieve the expected efficiency and security, what is your plan?
What's the plan?
In the case that your proposed crypto system do not achieve the expected efficiency and security level, then what is your plan? If they are not good enough.
Actually, from the first objective, I already show that my operation is less and less operation from the existing system. Yeah, it's less operation, so it's more security guarantees.
Guaranteed. But
Yes.
but you said that objective 2 and 3 are not yet done.
Yeah, I'm start with it. Yeah, I'm not finished, but we start with this.
Okay, so it's not yet complete. Okay, Hebah, I can see you are progressing good enough. So this is your second year, right?
Yes.
So I think you have enough time to complete objective 2 and objective 3. In the case that the new proposed crypto system is not good enough, you still have a time to do the modification. Okay?
Yes.
Okay, so I think that is all from me. Thank you very much and all the best.
Thank you so much. Thank you.
Mr. Go.